Hey, my name's John Graham. I lead the application engineering team in topology, and today we're going to talk about end effectors and why end effectors. Well, we've actually had several of our users and several of our customers ask how we can help out in the way of doing particularly two things: optimizing these and lightweighting end effectors. And so some of their inspiration of what I wanted to show you, I can kind of capture in a video I found on YouTube. So as you watch part of this, you'll notice that an end effector, in this case, grabbing something, compliance is really what's important. You need the end effector to not exactly be terribly strong, but just grip around something. And so that's the effect in that short video that we're going for. So I went out to GrabCAD and found what I thought was kind of a representative part or something that I can work with. This comes from an individual by the name of Mark Thomas. Sorry if I'm mispronouncing that. But I thought Mark had a good representative end effector, and he actually did a pretty good job of lightweighting this and finding out where stresses were and where deflections were. And so I went ahead and downloaded this, and this is kind of the model that I want to work from today. And so this will be very brief, I think, but I'll show you two different things that could be mutually exclusive if you want, or you could combine these two aspects together. But for the point of demonstration today, I'll keep them kind of separate. So this is what you might see in an assembly for an end effector, right? So you've got your robotics and the arms at the end that may grip something. And just as you saw in that video, the idea might be that you have some kind of an object here in the center, and where I'm highlighting in blue, this is where you need some kind of compliance. You need these devices to flex. And my model is a little bit different than what you saw earlier, but what you might have where I'm highlighting in green is the bottom of these might come together, and that's your stopping point. So you want everything in the red area, or the red and blue, to flex. All right, so let's jump into one of the two files, and then we'll move on. So let me just highlight the original part that Mark had. And if we're talking about compliance, that really isn't going to do it. So I went ahead and defeatured this in a CAD system and said, let's take that area in blue, and that's the zone in which we want to work with. So what does nTop have to offer in the way of optimization here? Well, the whole idea is that this is a tool in which you can go from just a large zone, as I have here in blue, to some kind of a finalized model that's complete with the lattices you want. But it's not just a finalized model we're after. Perhaps this is a family of parts or a design of experiments where you want to determine which is the best one. And so this is where nTop really shines. So what I did is set up this workflow that has all these parameters. So the fin thickness, and let's just start playing with these and kind of go back to what I might call the original. So I've got a fin thickness of 5 millimeters, an angle of 0, and let's actually drop this radius down. And so those are the main three parameters I want to play with that are going to have an effect on this. So you can obviously tell that things look a bit different. And so this could very well be a model that you decide to export out and run some kind of a simulation on it, or maybe even print it in a flexible, I don't know, polyurethane or so, and run some actual tests and see what the compliance looks like, and if your forces are too strong or too high. So again, you can put in any values that you want. Again, this is set up just as a simple workflow. All the parameters are plugged into, and the model just rebuilds like that. One thing I want to draw your attention to, and we've shown this on several demonstrations, a lot of them, is you tend to get, as my understanding is, you tend to get a lot a delaminating, if you will, of the lattices to the skins. And so one way to get around that is to put some radii between the lattices and the skin. Well, we automatically just do that when we merge or blend things together, and I've gone to a higher resolution rendering so you can see that effect. But obviously you've got these beautiful rounds. And this isn't that many. Okay, we're talking, maybe 30 junctions around here. But what if you have, I don't know, 30,000 lattices or edges that are going to be meeting the skin? Well, that could be problematic. So you have to make sure that you can account for that. nTop does a wonderful job at it. All right, so that's the first example, and I could keep going. But I think you get the idea. Design of experiments could be could be generated. You run the simulation on these and determine the best one. And of course, we have other tools to let you actually spit out more than one of these models at a time and generate several files if you want to and run a simulation on them. You can actually do the simulations here and nTop if you wanted to. Okay, the second model is, let's go to this guy. All right, so we're starting off again with that original file that I downloaded. And again, this individual did a great job, I think, of lightweighting this and putting some, fairly prismatic faces in and eliminating weight. But I said, well, let's use some native topology optimization and then topology to take, again, this area in blue and optimize that by dropping as much material as we can. So I'll kind of walk you through sequentially what I did very briefly, and I think it'll make perfect sense. I split out what would be the outer frame. And let's see, this is the full bracket. I think somewhere in here I've got the body that represents the region. Yeah, there it is. That could be topology optimized. And then a couple of faces that represent the forces and the fixed area. Actually, one force on the far left and the two circular faces I'm calling are going to be fixed. So I set up the topology optimization. If you want to see the nodes, you can see them right there. And when you look at the results of this, it looks like many topology optimization results are going to look. It's a bit jagged everywhere. If I run through the threshold slider and dictate which elements get dropped and which get included, you see a big difference there. A problem that people have with topology optimization is, okay, it looks good. It's a pretty picture. What do I do with it from there? How do I decide on what objects to select and what not to? And then what do I do with it after? Well, the second part is what I want to have a little more focus on, is what do you do with it once you decide what's good? Well, the first thing that you're going to need to do is smoothen a body. Well, we have an algorithm just automatically does that. It'll run through several iterations. If you want, you can smoothen this to 1 degree or another after selecting which threshold looks good to you and what fits your criteria. The second important thing that we'll do in this workflow of getting a finalized model is actually shell something out. And this is an extremely impressive capability that we have. And if you've seen us show anything on nTop before, you've undoubtedly seen this, or hopefully you have. This is nothing straightforward as far as the topology goes on this file, but we've managed to shell this out. And I've actually shown you what I might call a simple shell, meaning a uniform wall thickness running throughout, but we could actually put a variable shell. And I didn't have time to do that in this model, but based on a distance, so if you want a variable shell from one direction to another, if you want to take in simulation data, either from here or an external source, and have that drive the variable thickness of this, you can do that. And the procedure for it is about exactly the same as what I did to make the uniform shell here. Okay, so the next step in this progression is you have a model that's been smoothened, that's been shelled. What do you do with it there? Well, many of our users have told us for quite a while, hey, John, we want to get this model back into our CAD system for one reason or another. And there's many ways to do it, but oftentimes people will want a boundary representation, or what we just simply call a CAD file representation, back in their system. Well, we can do that. That's no simple task, effectively taking what could be a complex mesh and turning that back into CAD data. And that's exactly what we have done. So you see these beautiful strips of boundary representation running throughout. One thing that's I want to draw your attention to in this is that you can't tell by looking at it. You'd have to go in and do some probably some other calculations and even notice it in a CAD tool, but all of these surfaces are curvature continuous. So you effectively have Class A surfaces, and you're not going to have ripples and strange effects if that's something that you're going for. I think that's just a icing on the cake and a little bonus you get when going back to a boundary representation. So let's kind of wrap this up. I took a boundary representation from the outside surfaces, and I separately did that for the inside surfaces as well. If I show, well, let's just show these two models here. Let's see, I'll do that one and this one, and I'll go to this view. Okay, You can see the outside representation, that mesh, and in blue, you see the result of the shelling. So I'm just highlighting these so you can see that there's, in fact, two different bodies going on, and I did two operations and exported those out. And we found for now, it's just a little easier to take those two distinct boundary representations, the outside and the inside, bring those separately into a CAD tool and merge it all together. And that's exactly what I've done. So I basically took three bodies here: the frame, the inside surfaces, and the outside ones. And I've merged them all into one. And of course, you could do this in any of your favorite CAD tools. I happen to know ANSYS Space Claim a little better than the others, so I brought this in here and in no time was able to merge these together. And there you see the uniform wall thickness as well. This is not simple geometry. Anytime you're working with topology optimized data, it's very organic in nature. Can be very rough. Of course, we smoothen that out, but the surfaces are just not that straightforward. But we're able to make sense of that and give you something very usable down the road. So that's all I wanted to show you. I promised I'd keep it a little bit short. Went longer than I thought, but if there's any questions, please type those in now, and I'm happy to answer them. And while you guys are typing in any questions, again, look for us every Monday, Wednesday, Friday doing these nTop lives where we're targeting to show you specific applications of how people are using nTopology software, nTop platform. We want to show you the value of what it brings, not just a training or a how-to. I will make these files available. There's no smoke and mirrors to this, so everything I've shown you, I will give you. And if you have nTopology, try it out yourself. If you don't, contact us and see about getting some kind of a trial or demonstration. We're happy to walk through specific examples with you. And yeah, that's about it. So I don't see any questions coming in. To me, that means I did a great job in explaining everything and no questions to ask. Probably not the case, but feel free to reach out to us if you have any, and we're happy to answer them. And yeah, I'll call it a wrap for today. Thanks for watching, everybody. I appreciate it, and have a great rest of your week.